Have you ever looked at a huge mountain and just wondered what's really going on inside? Well, it turns out engineers have a way to figure that out. They essentially give it a report card. And today, we're going to dive into this hidden world of geological grading and see exactly how they do it. I mean, it's a massive question, isn't it? Before you even think about building a road or a railway or a giant dam, you absolutely have to know if the ground you're building on or tunneling through is stable. You can't just cross your fingers and hope for the best. You need data. You need a system. You need a way to score the rock itself. And this is that system. This is the Rock Mass Rating Chart, or RMR for short. Now, I know what you're thinking. It looks a little intimidating, right? A whole wall of numbers and geological terms. But trust me, by the end of this, you'll be able to read this thing like a pro. We're going to break it all down together, one step at a time.
So here's our game plan. First, we'll talk about what this report card for rock really is. Then we'll get into the 5 key things they measure to get a score. After that, there's a crucial final adjustment for the angle. Then we'll see how that score turns into a grade, and finally, what those grades actually mean in the real world.
All right, let's start with the big picture. Just think of the RMR system as the most important standardized test a rock will ever have to take.
At its heart, the RMR system is this really brilliant tool that takes super complex geology and boils it down to a single practical number. It lets engineers classify the quality of a rock mass, which is just a fancy way of saying all the rock in one area, with all its cracks and weaknesses included. And with that score, they can predict how the rock is going to behave, so they can design way-safer tunnels, foundations, and slopes.
Okay, time to get our hands dirty. The foundation of this whole system is a score that you calculate from 5 key parameters. So, we're going to walk through them one by one, and we're going to score a made-up piece of rock to see exactly how this works.
These are basically the 5 subjects on our Rock's Big exam. Each one gives us a vital piece of the puzzle, everything from the raw strength of the rock itself to the water that might be flowing through its veins. So, let's start grading.
First up, rock strength. This is pretty straightforward. It measures how much pressure the solid rock can handle before it just crushes. Our example rock here has a strength of 150 megapascals. So we look at our chart and we see that a strength between 100 and 250 megapascals gets a rating of 12. Boom, that's our first score.
Next up is something called drill core quality, or RQD. This basically answers the question, how fractured is this rock? Engineers drill out this long cylinder of rock, and the RQD is just the percentage of that core that comes out in solid chunks. So our rock has an RQD of 80%. Looking at the chart, that puts us in the 75 to 90% range, which gives us a rating of 17. So our running total is now 12 plus 17, which is 29.
Parameter number 3 is all about crack spacing. Are the cracks in the rock mass all bunched up together, or are they nice and far apart? And let me tell you, farther apart is way better. Our rock's cracks are spaced about 1 meter apart. On the chart, a spacing like that gets a rating of 15, so we add that to our score, bringing the total up to 44.
Now we need to look even closer at those cracks. What are they actually like? Are the surfaces smooth and slippery, or are they rough and jagged? Are they clean, or are they maybe filled with some gunk like clay? Our rock has slightly rough and slightly weathered crack walls, and this is actually pretty good. It means the surfaces have some friction to them. According to the chart, this condition gets a solid 20 points, so our total jumps all the way up to 64.
Okay, our final parameter is water. Water is incredibly powerful. The pressure from water inside rock cracks can actually push them apart and make the whole rock mass a lot weaker. Our rock is just described as damp, so it's not totally dry, but it's not dripping or flowing with water either. The chart gives a damp condition a rating of 10.
So let's add it all up. Our previous score was 64. We add 10 for the groundwater, and that gives us a subtotal of 74. Hey, that's a pretty good score. But we're not quite done. There is one more crucial final adjustment we have to make. This last step is all about direction. It turns out the way the cracks are oriented compared to the direction you're trying to tunnel makes a huge difference. You really have to account for your angle of attack. Think of it like cutting a piece of wood. If you tunnel against the grain of the rock layers, it's strong. That's a favorable condition, and you only have to subtract a couple of points. But if you tunnel along the grain, well, you're basically creating a nice, smooth path for big blocks of rock to just slide right out. That's very unfavorable, and you could lose 12 points. For our tunnel, the orientation is rated as fair, So if we look back at our chart, that means we need to subtract 5 points. So let's do the final math. We take our subtotal of 74, we subtract 5 because of that joint orientation, and we get a final rock mass rating of 69. And there you have it. We've officially graded our mountain.
So we have our number, 69. But what in the world does that actually mean? Well, now it's time to translate that score into a final grade, an official classification. And here we go. The RMR system is broken down into 5 classes. As you can see, our score of 69 falls squarely into that 61 to 80 range. That means our rock is officially designated as Class 2 good rock. Not perfect, but definitely solid stuff.
Now, this isn't just some academic exercise. That good rock classification has huge, real-world consequences for how engineers are going to approach construction. It dictates everything from the cost of the project to the safety measures they have to take.
And this right here is why it matters so much. Just look at the staggering difference in what they call stand-up time. A tunnel in Class 1 rock can stay open without any support for decades, but a tiny little opening in Class 5 rock might collapse in half an hour. For our Class 2 good rock, the chart tells us a 10-meter wide tunnel should be able to stand on its own for about a year. And having that knowledge is the difference between a successful project and a potential disaster. So, that's the whole journey. We went from a really complex-looking chart to a single, powerful number. The rock mass rating system takes the messy, variable, uncertain world of geology and translates it into the clear language of engineering. It's how we build with confidence, both on and deep inside the earth. So the next time you drive through a tunnel or see a massive dam, you'll know about the incredible amount of calculation that went into understanding the very rock it's built on. The world around us isn't just scenery, it's a massive engineering puzzle just waiting for us to solve it.